the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is the second to final section that I cover in my linear algebra course here at CRC. In this video, we're going to start a conversation about diagonalization of symmetric matrices. Now, if you followed along in my video series, I really haven't mentioned too much about symmetric matrices as of yet. However, at this point, we're going to introduce them, and then we're going to do some diagonalization of them. So let's talk about that here. The definition of a symmetric matrix is that a matrix A is symmetric if it is true that A is equal to its transpose. Now, this is going to be incredibly obvious when you start seeing symmetric matrices. For example, this matrix right here is symmetric because if I were to write A transpose, well, our first column becomes our first row, but notice that matches the first row of A itself. The second column of A becomes the second row of A transpose, but again, notice that the second row of A transpose is actually the same as the second row of A. And finally, the third column of A becomes the third row of A transpose, but again, if you look at A transpose versus A, their third rows are identical. Now, a quick visual way of seeing that you have a symmetric matrix is that you have a sort of mirror image about the main diagonal. This is the main diagonal right here. Those entries actually do not matter too much for this conversation, but the mirror images of the entries across that main diagonal are the same. So 2 is the same as 2, 3 is the same as 3, and 5 is the same as 5. That's really a quick kind of glancing effort at noticing you have a symmetric matrix. Now, because A has to equal its transpose, A is going to be a square matrix. So again, if I hand you a symmetric matrix, you know immediately it is a square matrix. Also, note this last little piece right here. A brief review of diagonalization is going to be very helpful here. And that's because when you normally talk about symmetric matrices, you're really very interested in similarity transformation, specifically diagonalization. That's incredibly helpful for some applications. So as a very brief review, remember a matrix is said to be diagonalizable if it's similar to a diagonal matrix. And remember, to be diagonalizable, a matrix must be square. And just to remind you, this is the same thing as saying that if A is diagonalizable, then there must exist a diagonal matrix D and an invertible matrix P such that P inverse AP is equal to that diagonal matrix. Now, since P is invertible, it is true that A is equal to P D P inverse. And we had discovered that the columns of P were the eigenvectors of A, and the corresponding entries along the main diagonal of D were the corresponding eigenvalues. And then P inverse itself was obviously the inverse of P. Now, normally I really don't like to use examples from the textbook. I usually try to avoid that so that if you're one of my students, you can just read the textbook and get extra examples on top of the examples that I do in lecture. However, I really like this example that the author set up. And to be very honest with you, it's just a temporary kind of intermediate example to showcase where we're driving this lecture. So let's go ahead and take our time to diagonalize this matrix right here. Remember, that's going to require us to find the eigenvectors of A and their corresponding eigenvalues. However, we have learned quite a bit since diagonalizing matrices, and one of the things we've actually learned is how to normalize vectors. So you're going to see a little bit of a change up as I go through and diagonalize this matrix. Once I get the eigenvectors, well, if let's just say v sub 1 is an eigenvector for A, then any non-zero scalar multiple of v sub 1 is also an eigenvector of A. Specifically, the normalized version of v sub 1 will be an eigenvector of A corresponding to that associated eigenvalue, lambda sub 1. So we're going to find the eigenvectors, then normalize them. That's a long-winded way of saying that. Now, hunting for the eigenvalues here, we find the characteristic equation is going to be lambda cubed minus 17 lambda squared plus 90 lambda minus 144. This is obviously a pretty terrible looking characteristic equation. However, that is how life works sometimes. We're going to go ahead and maybe use the rational roots theorem and present ourselves with some possible rational roots for this equation. Remember, the rational roots theorem says take all the factors of this constant term, negative 144, and divide them by all factors of the lead coefficient, which is just 1. So really, my candidates for roots are going to be plus or minus 1, because that's always a factor of a number. And then since it's even, plus or minus 2. Then since the sum of the digits is actually divisible by 3, this is also divisible by plus or minus 3. And you can go a lot further with this. Obviously, it is actually divisible by 4 as well. And I'm just going to put plus dot dot dot. If I need to go further, I will. But you're going to see me speed up the video right now while I check for roots. Now, again, I stole this from the textbook, but you may not use the same textbook that I use, so it would be very beneficial for me to just remind you of how to check for roots using the rational roots theorem. Well, the first thing I'm going to do, honestly, is just try to plug in 1 or negative 1. If you plug in 1, you'll get 1 minus 17 plus 90. So what is that? 91 minus 17. And if you lose another 144, there's no way that'll become 0. So I know the positive 1 is out of the question. Now we're going to try to plug in negative 1. If you plug in negative 1, you'll actually get a negative 1 minus 17, so that's negative 18, minus 90 minus another 144. I immediately know negative 1's also not a root or a solution to that equation. Now you could do the same trick pretty quickly using 2 and negative 2, but in this case, I'm actually going to go ahead and just do synthetic division for those. The black ink will be permanent throughout this process. The blue ink is my efforts, my tries here. So we're going to try to show that 2, positive 2, is a root of this function really on the left-hand side, or in other words, a solution of that equation. All right, so 2 didn't work because we get a remainder that's non-zero. So 2 is definitely not a solution of that equation. I'll go ahead and try negative 2 now. And you can always pause the video and try this yourself to see if you get the same remainders or solutions that I get. Notice in this case, I knew it was going to be negative 200 and something. I don't bother actually doing the full mathematics because I know negative 144 and lose some more is not going to turn into 0. So I also know that negative 2 is not a root. So plus or minus 2 do not solve that equation. Off we go to the next possible solution. And I should say before I start this, that the fact that this is a cubic means I really only need to do synthetic division until I get a single root. Once I get a single root, I will be able to factor this and I'll have a quadratic, and I can factor a quadratic pretty easily. So let's go ahead and try 3. All right, so 3 is definitely a solution to this equation. That is, lambda minus 3 is a factor of the left-hand side expression. What's left over after you factor out lambda minus 3 is 1 lambda squared minus 14 lambda plus 48. That's the nice thing about synthetic division. And we happen to know two numbers that multiply to 48 and add to a negative 14 are negative 6 and negative 8. Well, that's very nice. We have 3 distinct eigenvalues. Let's go ahead and write those down actually. There are our eigenvalues for this given matrix up above. It took us a while to get there, but we're done with it. Now we'll go ahead and find their associated eigenvectors. All right, there we go. That wasn't too terrible. Now we're going to go ahead and do the same thing for lambda sub 2, which is equal to 6. And there we have that right there. I'll go ahead and write the eigenvector. And I wrote that by multiplying, or basically allowing x sub 3 to be 2. It just made it a little bit nicer to not have fractions. Finally, lambda sub 3 being 8. Let's go ahead and write that in. All right, there's our third eigenvector. Now I'm actually going to clean this up because I want to use this page to finish this diagonalization process. So let me go up to the top again. All right, So I have everything cleanly written right here. And obviously, just from our previous experience diagonalizing matrices, we could right now go ahead and write A as the product of three matrices. One being P, which is the matrix having these eigenvectors as its columns. The next one being D, which is the diagonal matrix having 3, 6, 8 as its diagonal entries. And finally, P inverse, which is just the inverse of P. However, as I mentioned before, if we have an eigenvector of our matrix A and that eigenvector is associated with the eigenvalue lambda, then any non-zero multiple of that eigenvector is also an eigenvector of A with the same associated eigenvalue actually, so nothing will change with the eigenvalue. What I'm going to do now is incorporate what we have been learning recently, which is normalization. So I'll take the normalized version of V sub 1, along with the normalized versions of the vectors V sub 2 and V sub 3. Again, these are still eigenvectors for the matrix A. Now watch what happens here. When I let P be the matrix whose columns are these normalized eigenvectors, I want you to notice something very special. First of all, of course, these columns are normalized. In other words, they have unit length. But also, if you took the dot product of any of these two columns with any of the other two columns, it would be 0. For example, the dot product of column 1 with column 2 is going to be -1 over root 18 minus another 1 over root 18, but you gain back 2 over root 18. If you were to take the dot product of columns 1 and 3, well, that'd be a -1 over root 6 plus 1 over root 6. Again, that's going to be 0. And finally, take the dot product of columns 2 and 3, you get a +1 over root 12 minus 1 over root 12 plus 0. Again, that will be 0. So this shows that all of these columns are orthogonal to each other. Not only that, but they're normalized. So these are orthonormal vectors. And we happen to know that a matrix that has columns that are orthonormal, that is a special matrix called an orthogonal matrix, and it has a very, very, very special property that P inverse is equal to P transpose. So remember, when you go to diagonalize a matrix, that diagonalization should be P times D times P inverse. However, in this very special case, because we normalized those eigenvectors and also because those eigenvectors were orthogonal to each other, which means that the matrix P is an orthogonal matrix, that means that P inverse in this very, very, very special case is P transpose. And that makes the mathematics a ton easier because we don't have to hunt for P inverse at all. By the way, I didn't really write it down, but the diagonal matrix D is still 3, 0, 0, 0, 6, 0, and 0, 0, 8. Even though we normalized those eigenvectors, their eigenvalues didn't change, so the diagonal matrix with those eigenvalues does not change as well. Now you might or might not be able to understand why I stole this example straight from the textbook, but I'll just say it right here. It is a very, very special situation where you have a matrix whose eigenvectors for their eigenvalues become orthogonal to each other. That's very special. There's something critically important about this matrix that allows that to be a truth. And it has something to do with what we just introduced at the beginning of this video, the symmetry of this matrix. Notice we have this main diagonal, but all the off diagonal entries are the same. They're just mirror images across that highlighter. And so this is a symmetric matrix. Now you might be thinking, well, I guess he's saying every time I have a symmetric matrix, it can be diagonalized this way where it's just P, D, P transpose, where P is the matrix consisting of the eigenvectors who have been normalized and they're immediately orthogonal to each other. Now, to be honest with you, it won't always work like this, but we can actually force it to occur. So that's what we're going to do in the next video. I hope this video has helped you out a little bit. It's just an introduction to symmetric matrices and kind of a preview of where we're going. In the next video, we're going to talk about orthogonally diagonalizable matrices. I hope to see you there, and I hope you have a wonderful day. Be a great human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.